In this video, we're going to cover the topic of crude oil, looking at fractional distillation, cracking, combustion, and the different pollutants produced by the burning of fuels. And free radical chemistry, looking at free radical substitution and the role of ozone in the atmosphere. Crude oil is a mixture of different hydrocarbons. A hydrocarbon is a molecule which contains hydrogen and carbon only, so there are no other atoms in a hydrocarbon except for hydrogen and carbon. Crude oil contains different lengths of hydrocarbon chains. You can have some shorter chains and some longer chains. We need a way to separate the crude oil into different chain lengths. Each of the different lengths of chains, also known as fractions, have a different use. In order to effectively use the different products, we need to have them separated. We can't use them as a mixture. The shorter chains are used for things like camping gas. The mid-length chains, ones about 8 or 10 carbons, are used in fuels, and the much longer ones are used as heavy-duty fuels, for example in big container ships. The first step in this process is to vaporise the crude oil, so you heat it to around 350 degrees. This turns it into a gas. This vaporised crude oil will then enter at the bottom of the column, and the largest hydrocarbons won't be vaporised and they'll be collected off as a liquid from this pipe at the bottom here. The column has a temperature gradient. This means it's a lot hotter at the bottom and colder at the top. As the vapour rises up the column, it's going to cool down. Each of the different chains will have a different boiling point. The boiling points of the alkanes get higher as the molecules get bigger. So the long chains have got a high boiling point, the shorter chains have got a low boiling point. This means that each fraction, each collection of chains of a similar length, will condense at a different temperature as the vapour rises up. The hydrocarbons with the lowest boiling points won't condense and will be collected as a gas at the top. We can also do this process in the lab. It's very similar to the industrial process we've just looked at, where the mixture of the crude oil will be heated, the vapour will rise up a fractionating column. However, this time, as opposed to lots of different side arms coming off the column, where all the different fractions can condense and come off at their set boiling point, instead the fraction with the lowest boiling point will reach the top of the fractionating column first, move down the condenser, be cooled and condensed and collected. You can then replace your collection flask and the fraction with the next highest boiling point will then reach the top and the process will repeat. We use the fractionating column here, essentially a long glass tube with little bits of like glass levels and layers inside, and this means it takes a longer time for the different fractions to evaporate. So you'll get them evaporating at different rates, with the one with the lowest boiling point evaporating first and the one with the highest boiling point evaporating last. Cracking is the process through which long hydrocarbon chains are broken down into shorter chains. We can break a long hydrocarbon down into an alkane and an alkene. This process is carried out because shorter chains are more useful and in higher demand. So from the process of fractional distillation which we've just looked at, we have lots of long chain hydrocarbons left over which there aren't much use for, and we have a lot of them. We need more shorter chains because they're more useful. We can use them for fuels. They're in high demand. We need a lot of petrol, for example. So we can take the long chains and break them into shorter chains. So for example, if I had this long chain alkane here, I could break it down into an alkane and into an alkene. You'll need to be able to write cracking equations for a variety of different alkanes. So for example, if we had C10H22, we could break that down into C5H12 and C5H10, noting the total number of carbons are the same and the total number of hydrogens are the same. It could also be cracked and broken down into C3H6 and C7H16. You might form more than one molecule, so we can crack C10H22 into 3 molecules, a C2H4, another C2H4, and a C6H14. This can be simplified though by writing 2 lots of C2H4. There are 2 different ways we can do cracking. There are 2 different methods you can follow. You can either use thermal cracking or you can use catalytic cracking. Thermal cracking uses a very high temperature, about 1000 degrees C. Catalytic cracking also uses a high temperature, but only about 500 degrees C. Thermal cracking uses a high pressure, about 70 atmospheres, whilst catalytic cracking only uses a slight pressure, slightly higher than standard pressure. As in the name, catalytic cracking uses a zeolite catalyst. This lowers the costs because the reaction can be done at a lower temperature, so lower energy is required, and the catalyst will speed up the rate of reaction as well. You need to know the name of the catalyst, so you need to know it is a zeolite catalyst which is used. Thermal cracking will produce a lot of alkenes, and catalytic cracking will produce aromatic hydrocarbons and alkanes. Aromatic hydrocarbons are molecules with a benzene ring. You'll learn more about those in year 13, but at the moment you just need to know the name of these kind of hydrocarbons as aromatic. Thermal cracking will produce the alkenes, as we've just mentioned, and these can be used as feedstock chemicals for polymerization. So we can turn all the different alkenes, for example ethene, into polymers, polyethene or polythene. And the products of catalytic cracking, those aromatic hydrocarbons and alkanes, are typically used in motor fuel. We're now going to look at the burning of fuels. So we're going to look at complete combustion first, and then incomplete combustion. Burning alkanes in an excess of oxygen will produce carbon dioxide and water. Excess oxygen just means there's more oxygen than we need for the reaction to take place. So for example, C3H8 will react with 5 molecules of O2 to produce 3 molecules of CO2 and 4 molecules of H2O. You need to make sure that you're quite happy to balance simple equations like this, and you can revisit the work you've done in your physical chemistry topics if needed to get some more practice at balancing equations. Another example might be C6H14 reacting with 9.5 molecules of oxygen, sometimes written as 19/2, because obviously 19/2 is the same as 9.5, and this would produce 6 molecules of CO2 and 7 molecules of H2O. So make sure you're comfortable with writing equations like this for any given alkane or hydrocarbon. Incomplete combustion is when alkanes are burnt in a limited supply of oxygen, and this produces carbon and/or carbon monoxide and/or carbon dioxide and water. Whether you produce carbon, carbon monoxide, or even some carbon dioxide will depend on how much oxygen is available. This process is less efficient than complete combustion, so less energy will be released through this process compared to complete combustion. So complete combustion is the preferable way to burn fuel. As before, you'll need to be able to write equations for this process. So for example, C5H12 could react with 5 molecules of O2 to produce 2 molecules of CO2, 3 molecules of carbon, and 6 molecules of water. Alternatively, it could react with slightly more oxygen, 6.5 moles of it, to produce still 2 moles of CO2, but this time 3 moles of carbon dioxide and still 6 molecules of water. If there was less oxygen available, maybe 3.5 moles of O2, instead it might produce 4 moles of carbon, 1 of carbon monoxide, and still 6 of water. We're now going to look in turn at 4 different pollutants which are produced from burning fuels. We'll look at the problems each one of these can cause. To start off with, we'll look at carbon monoxide. This is the chemical formula CO. It is a poisonous chemical. Because it binds to the same site as oxygen does on a hemoglobin molecule. It also binds more strongly, so it's binding to the molecule in your red blood cells which carry oxygen around your body. If the carbon monoxide is binding to the hemoglobin rather than the oxygen, this means oxygen is being prevented from being carried around your body, so your body cells can't use the oxygen, and ultimately this is what causes carbon monoxide poisoning, which you can sometimes get from a faulty boiler or from a disposable barbecue. This means that if you get carbon monoxide poisoning, your red blood cells have got carbon monoxide bound to them rather than oxygen, and it'll cause you to faint, then eventually fall into a coma, and then you would die because your body wouldn't be getting any oxygen to all its cells. Nitrous oxides are also produced as a pollutant from burning fuel, and they have the general formula NOx. This means that the oxygen could be several different values. You could have nitrogen oxide, NO, nitrogen dioxide, nitrogen trioxide. We're going to group all of these together. They're formed in car engines when oxygen and nitrogen from the air react together under the high temperatures you can only get in the car engine. It's why the oxygen and nitrogen in the air don't normally react together. It can also cause acid rain, and we'll have a look in a moment when we look at sulfur dioxide about what acid rain is and how it is formed. You need to know the equations for how nitrogen oxides are formed. So the first one is nitrogen reacts with oxygen to form 2 molecules of nitrogen monoxide, and then 2 molecules of nitrogen monoxide can react with another molecule of oxygen to form 2 molecules of nitrogen dioxide. So you need to learn and remember these 2 equations. Ozone is another pollutant produced from fuels. It has the chemical formula O3. And it can cause eye irritation at ground levels and breathing difficulties if you were to breathe it in. We're going to look at the role that ozone plays in the atmosphere in more detail towards the end of this video. Finally, we're going to look at sulfur dioxide. Sulfur dioxide has the chemical formula SO2. And it's formed when fossil fuels are burnt which contain sulfur, which is an impurity in the fuel. The sulfur will react with the oxygen in the car engine when the fuel is being burnt, and this then produces sulfur dioxide gas. As mentioned earlier, nitrous oxides and now sulfur dioxide can cause acid rain. This starts off by these two gases entering the atmosphere. These gases can then dissolve in the moisture in the atmosphere. They can essentially dissolve in the clouds. And this is what acid rain is, because when we dissolve sulfur dioxide or nitrous oxides, they will form sulfuric acid and nitric acid. So when these gases enter the clouds, they dissolve in the water vapour in the clouds, and they will form acids. Sulfur dioxide and nitrous oxides forming sulfuric acid and nitric acid. This then falls as acid rain, which can destroy trees and vegetation and crops. It can damage limestone buildings and statues, and it can kill fish in lakes or ponds. We're now going to quickly look at a few different ways we can remove pollutants from the environment or from the source where they're created. Cars have catalytic converters inside of them designed to remove some of the pollutants we've just looked at during the combustion process. Ideally, the majority of the fuel which is burnt will be turned into carbon dioxide. However, as we've looked at earlier, incomplete combustion can happen, meaning that we will get some carbon monoxide produced during the combustion process. We also know that in the car engine, nitrogen and oxygen can react together to ultimately form nitrogen oxide. The catalytic converter enables the nitrogen oxide to react with the carbon monoxide produced during incomplete combustion. So any of this process here, which doesn't happen during complete and produces carbon monoxide instead, can then react in the catalytic converter with the nitrogen monoxide, and that will form two lots of carbon dioxide and nitrogen gas. The advantage of this process is it prevents nitrogen oxides and carbon monoxide being released into the environment. Obviously, carbon dioxide is a greenhouse gas and not ideal for the environment, but it's a much safer gas to be coming out of car exhausts, especially at ground level where people could be walking past, than carbon monoxide and nitrogen oxides, which are much more harmful. Sulfur dioxide can be removed from power stations before it is released into the atmosphere. Calcium carbonate, also known as limestone, or calcium oxide, is mixed with water to form an alkaline slurry. This then reacts with the sulfur dioxide, which can be considered acidic, removing it, leaving calcium sulfate instead. You need to know and to be able to write the equation for this process. Burning fossil fuels releases carbon dioxide, a greenhouse gas. Greenhouse gases absorb some of the infrared radiation leaving the Earth and then re-emit this back towards the Earth, keeping it warm. This is known as the greenhouse effect. This is a natural process which enables the planet to have a habitable temperature. The problem is where too much of this process happens and causes the temperature to rise too much. Increasing levels of carbon dioxide increase the amount of the greenhouse effect which is happening, and this is what we refer to as global warming. We're now going to look at the topic of free radical chemistry. A free radical is a species with an unpaired electron. It's not something you commonly see in chemistry. These are all examples of free radicals we're going to come across looking in this topic. We can see that they are a free radical because we draw a dot on the atom which has an unpaired electron. Again, this is something not typically seen in chemistry. This is the only topic through which you're going to use radicals. So where there is one, we denote it by drawing the dot on the atom which has an unpaired electron. Free radicals are formed when a covalent bond splits equally, giving one electron from that shared pair of electrons, which is the covalent bond, to each atom. This makes the molecule very reactive, Electrons want to be in pairs, so if it is unpaired, it's going to try and pair up with something, so it'll try and do any reaction it can to get that electron paired up. So any species with an unpaired electron, any free radical, is a very reactive molecule. So to imagine how they're formed, if we look at this chlorine molecule with the bond drawn here, and remembering this bond represents a shared pair of electrons. If the bond was broken, represented by the arrows coming out from the middle of the bond, one electron from each half of that bond would go to one each of the atoms, leaving us with two chlorine radicals, each of them having one of the electrons from this covalent bond. We're going to start off by looking at the overall reaction when we add one of these free radicals to a molecule. There are several different stages we're going to cover, so we're going to start looking at it from a broad sense. UV light is needed for the reaction to happen. This causes the initiation stage to happen, which we're going to look at in a moment. The overall equation for this process involves an alkane reacting with a molecule of halogen, so in this case, for example, Cl2, with UV light. The UV light is essentially a catalyst, it's not an actual chemical substance, so it is written over the arrow. This will substitute one of the hydrogens on the hydrocarbon for one of the halogen atoms, and then leaving that hydrogen attached to that halogen. This is a generic process, it's a process that you can learn, so this will always be the general overall equation process. The alkane, or the hydrocarbon, will react with a molecule of halogen with UV above the arrow. We will substitute one of the hydrogens for one of the halogen atoms, and the remaining hydrogen will then be bonded to the other halogen atom. And this process can keep on repeating. So the molecule we made in the first step can then react again with another molecule of our halogen, substituting another one of its hydrogens, so going from 3 hydrogens now to 2 hydrogens, adding on another chlorine, then producing another molecule of HCl. This reaction can then happen again, so the product we've made here, CH2Cl, can then react with another halogen molecule, substituting another hydrogen for a chlorine and producing another molecule of HCl. And this process can happen a final time so that all of the hydrogens have been substituted for chlorines. The overall equation for this process would be our CH4 molecule reacting with 4 lots of chlorine to produce CCl4 plus 4 molecules of H2O. You could be asked, and we'll practice this in a moment, of writing an overall equation for any given conversion. So either adding on 1 halogen, you might be asked to add 2 on, to add 3 on, or like in this overall case, adding 4 on. We can see here the equation is clearly balanced because every 1 hydrogen we substitute requires 1 molecule of chlorine to add one of those chlorine atoms onto our alkane, leaving us with 1 molecule of HCl at the end for each time this process has happened. So for example, we might be asked to write the conversion of going from CH3CH3 to CH3CHCl2. The trick to doing this is to realise how many halogens have been substituted. Well, we've got no chlorines in this molecule here. We've got 2 chlorines in our target molecule, so the overall equation must involve the substitution of 2 chlorine molecules. So this would be our overall process. We've substituted 2 hydrogens for 2 chlorines, so we must need 2 molecules of chlorine, because for each molecule of chlorine we add one of them, or we substitute one of them onto our alkane, and we produce 1 molecule of HCl. So to add 2 atoms of chlorine onto our target molecule, we've got to use 2 molecules of chlorine here and producing 2 molecules of hydrochloric acid as well. This is the overall equation, but each time this process happens, there are actually 3 separate steps happening, which we're going to learn about in detail now. These are the initiation step, the propagation step, and the termination step. The initiation step produces the free radicals. UV light in the upper atmosphere, coming from sunlight, has enough energy to break the chlorine-chlorine bonds. We call this photodissociation, the light causing the bond to break. The bond will split equally, so each atom will have an unpaired electron. We'll write the equation like this, showing the chlorine molecule reacting or being broken apart by the UV light to produce 2 chlorine radicals. So this is the equation you'd need to write down for the initiation step. You could also be asked to write free radical equations for other halogens, so the process would work exactly the same with, for example, bromine instead of chlorine. 1 molecule of bromine would be photodissociated by the UV light, producing 2 bromine radicals, making sure we clearly add the dot somewhere on the atom to represent that it is now a free radical. The next stage is called propagation. This is where the free radicals are used up and reformed, and this is how we convert our alkane into a halogenoalkane. There are usually 2 propagation steps. In all the examples we're going to look at in A-Level Chemistry, you'll have 2 propagation steps during this process. What happens in the first propagation step is that a chlorine radical will attack the alkane, it will take a hydrogen from the alkane, leaving an alkyl radical. So it might be, for example, a CH3 radical. An alkyl radical just means the alkane which has now been turned into a radical. The second stage involves the alkyl radical attacking another molecule of halogen, so for example another molecule of Cl2, taking a chlorine from that Cl2, forming a halogenoalkane, and then reforming the chlorine radical we started off with in the first step. So the chlorine radical is essentially a catalyst in this process. It's used up in the first propagation step, reformed in the second, so this chlorine radical can keep on going through this process, turning our alkanes into halogen alkanes. We'll now have a look at some equations to demonstrate this. So in this first propagation stage, the chlorine radical removes a hydrogen from our alkane, forming hydrochloric acid, and now leaving the alkyl radical, in this case a CH3 radical. In the second propagation step, the alkyl radical reacts with a new molecule of Cl2. It will take one of the chlorines from the Cl2, forming CH3Cl, and leaving that chlorine radical left over, so it can then start the process again with a different alkane. This approach is very formulaic. We can see the same pattern in each of the examples. The chlorine radical, or the halogen radical, taking a hydrogen from the alkane, forming HCl and leaving the alkane radical. The alkane radical will then react with a new molecule of halogen, forming a halogenoalkane and leaving another halogen radical left at the end. So in this example here, a molecule of propane is going to react with a halogen radical, in this case a chlorine radical again. The chlorine radical is going to take a hydrogen. It's taking hydrogen from the middle carbon, so leaving the middle carbon with a radical, and we always make sure to draw the dot on the atom which has lost the electron as opposed to the molecule as a whole. So the dot here signifies that this carbon has got an unpaired electron, which makes sense because it's lost one of its hydrogens. The chlorine, having taken that hydrogen, has now formed HCl. The second step follows exactly the same pattern as the example we looked at a moment ago. The alkyl radical will react with a new molecule of Cl2. It's going to take one of these chlorines, leaving a chlorine radical by itself, which again will then start the process again because the chlorine radical is a catalyst. It's really important to make sure that in propagation steps you always have the same number of radicals on each side. If you notice, we've always got one radical on each side of the equation. There's one on the left side, one on the right side, one on the left side, one on the right side. This final example will again follow the pattern we've looked at. This time we're starting off with a halogen alkane, which is fine. You could be asked to show the second or third step in the process. So the chlorine radical is going to take a hydrogen from our starting molecule, leaving the alkyl radical, and the chlorine has now got the hydrogen it's stolen attached. In the second stage, our alkyl radical will react with another molecule of chlorine, taking one of the chlorines, so we've now gone from being Cl to Cl2, and leaving us a chlorine radical at the end again to start the process. The final stage is called termination. This is where two free radicals will combine. When the two unpaired electrons come together, they will form a new covalent bond, so the two unpaired electrons become paired, and therefore the new molecule will be much less reactive because it will no longer have an unpaired electron. It's important to note that to get the marks for a question like this, it is not just the reverse of initiation. You can't just write the initiation reaction backwards. You'll need to use a different set of radicals combining than that were present in the initiation process. So for example, you might have two methyl radicals come together to form a molecule of ethane, putting two radicals together like this. You might react one of the methane radicals with a chlorine radical to produce chloromethane. We couldn't use the equation in yellow because that would just be the reverse of the initiation process, a chlorine splitting apart to make two chlorine radicals. Typically, a question will ask you to write a termination step to give a desired product. So the question might ask you to write a termination reaction to produce a molecule of ethane. Or the question might ask you to write a termination reaction to produce a molecule of chloromethane. And you would have to look at the question, look at what radicals were present through your initiation and your propagation steps, and once you've identified what radicals you've got, decide which radicals you can put together to create the desired product the question is asking for. We're now going to work through three examples. For each of these, we'll need to give the overall equation, the initiation step, both propagation steps, and in an example, termination step. So in this first reaction, we're going to convert CH4 methane into CH3 chloromethane. So the overall reaction is just substituting one hydrogen for one chlorine. As we're just substituting one hydrogen, the overall equation is relatively simple, reacting methane with one molecule of chlorine to form one molecule of CH3Cl, our target molecule, and one molecule of HCl. We'll need to write an equation for the initiation step. And given we're adding chlorine in this case, it'll be a molecule of chlorine being broken apart by UV light to produce two chlorine radicals. We'll then write the two propagation equations for this process. The first of these being the chlorine radical, removing a hydrogen from our alkane, giving us our alkyl radical and HCl. The second propagation equation being the alkyl radical, removing a chlorine from a new chlorine molecule to form chloromethane and reforming the chlorine radical. Finally, we'll need to write an example termination equation. In an actual question, you might be given a target molecule to produce this way, but we'll just look at a couple of examples you could use. So you might combine a methyl radical with a chlorine radical to produce chloromethane. Or you might join together two methyl radicals to form ethane. So in this case, we've given the overall equation for the conversion, written out the initiation step, both propagation steps, and you could just write one of these termination equations. In this example, the question wants us to write the overall equation for the reaction of methane to trichloromethane, so adding 3 chlorines on, and to give the initiation, propagation, and termination stages for the step going from chloromethane to dichloromethane. So during this process, we'll produce some chloromethane, which will then convert into dichloromethane. The dichloromethane will then be converted into trichloromethane, but we only need to write the initiation, propagation, and termination steps for this particular part of the process. You don't have to do initiation, termination, propagation for all 3 steps. We're just going to look at it for this one here, which the question is outlined, but we'll need to give the overall equation for the entire process. So as we are adding on 3 chlorines, we're substituting 3 hydrogens for 3 chlorines. We're going to need to use 3 molecules of Cl2 to give us our target molecule. Given we've used 3 molecules of Cl2, we're also going to produce 3 molecules of HCl as our byproduct. We'll now write the initiation equation. We're substituting chlorine in this reaction, so 1 molecule of chlorine will be photodissociated by UV light to form 2 chlorine radicals. We're now going to write the propagation steps for this process here. So the propagation steps to convert chloromethane into dichloromethane. The first step in propagation, as always, is the chlorine radical removing hydrogen to form HCl, leaving us with our alkyl radical. The second stage is our alkyl radical reacting with a new molecule of chlorine to take chlorine from this, so in this case forming dichloromethane and leaving a chlorine radical at the end. Again, the chlorine radical is a catalyst, so we'll repeat this process on and on and on. We'll now need to give an example termination equation. So in this case, we might react together 2 of these radicals here to form CH2Cl, CH2Cl. Again, for this generic example, as long as it's not a reverse of initiation, that's not a problem, but the question might ask you to write a termination for a specific target molecule using whatever radicals you have available. Our final example wants the overall initiation, propagation and termination equations for the conversion of propane into 2-bromopropane. Our overall equation is pretty straightforward. We're substituting 1 hydrogen for 1 bromine, so we're going to use 1 molecule of Br2 in this process, producing 1 molecule of HBr as our byproduct. So for the initiation step, we're going to photodissociate 1 molecule of bromine using UV light written over the arrow to form 2 bromine radicals. It's exactly the same as the chlorine we've looked at in previous examples. We're now going to write the propagation steps. So in the first stage, the bromine is going to take a hydrogen off our alkane to produce our alkyl radical and HBr. In this case, we need to be careful which hydrogen we're going to remove. Our target molecule, which the question asked us to form, had the bromine on carbon 2. So we need to make sure we remove a hydrogen and form the radical on carbon 2. If we removed a hydrogen from the start or end of the molecule and had the radical on carbons 1 or 3, we would end up forming 1 bromopropane as our final product and not 2 bromopropane. So when you've got a molecule like this with say more than 2 carbons, you've got to be careful to make sure you're removing the hydrogen and adding the radical to the correct carbon. Otherwise, the process is exactly the same as all the other examples we've looked through so far. And the final propagation step is just the same as we've looked at previously. The alkyl radical will take a bromine off a new molecule of bromine, forming our desired halogen-alkane, and leaving a bromine radical at the end as the byproduct, which will then catalyse more reactions. We'll need to write an example termination step, which in this case could just be the alkyl radical we formed in the first step, reacting with a bromine radical, which is just a different way of forming the target molecule we're trying to make in the first place. We're now going to look at a chemical called CFCs and the effect they have on the environment. A CFC is a hydrocarbon where all of the hydrogens have been replaced with either fluorine and/or chlorine atoms. We call these chlorofluorocarbons, CFCs. So for example, this would be a CFC, as all the hydrogens have been replaced by chlorine or fluorine atoms. This molecule would be called trichlorofluoromethane. Before we look at the problems that CFCs can cause in the atmosphere, we need to look at the role of ozone in a little bit more detail. We looked at ozone as a pollutant in the lower atmosphere earlier. We're now going to look at its role in the upper atmosphere. It still has the same chemical formula, O3. Ozone is formed naturally in the environment up in the atmosphere when oxygen is broken down by UV light to form free radicals. An oxygen molecule is broken down by the UV light to form 2 oxygen radicals. Another molecule of oxygen will react with one of those oxygen radicals to form O3. You need to be able to know, recall, and write these equations. The carbon-chlorine bonds in CFCs are broken by UV light, forming chlorine radicals, very similar to the initiation reactions we've looked at earlier. So, for example, CCl3F under UV light will form a radical here and a chlorine radical. This chlorine radical will catalyse the decomposition, the breakdown of ozone. The chlorine radical will react with ozone to form O2 and a ClO radical. The ClO radical will then react with another molecule of ozone, forming 2 molecules of oxygen and a Cl radical. The Cl is a catalyst here. We can see it's used in the first step and then regenerated at the end. So 1 chlorine radical can decompose essentially an unlimited amount of ozone. The overall equation for this is 2 molecules of ozone being broken down into 3 molecules of O2. You need to again be able to know, write and recall these equations here, so you need to learn these off by heart. We're now going to look why this is a problem. Why is it an issue that chlorine radicals can break down ozone into oxygen? Ozone in the upper atmosphere acts as a chemical sunscreen. It absorbs harmful UV radiation, stopping it from reaching us. This UV radiation could cause skin cancer. CFCs are pretty unreactive, they're non-flammable, and they're non-toxic. They used to be used in fire extinguishers and propellants in aerosols and as the coolant gases in fridges. They were also added to foam plastics to make insulation and packaging material, so they were used quite frequently in the 50s and 60s for all these kinds of purposes. In the 1970s, research by several different scientific groups demonstrated that CFCs were causing damage to the ozone layer in the atmosphere. The advantages of using CFCs, them being unreactive, non-flammable, non-toxic, couldn't outweigh the environmental problems they were causing, so they were banned. They were causing a hole to form in the ozone layer, therefore allowing the harmful UV radiation through. Chemists have since developed safer alternatives to CFCs which contain no chlorine. We can use HCFCs, hydrochlorofluorocarbons, and HFCs, hydrofluorocarbons, which are less dangerous than CFCs as they have less chlorine atoms in them, therefore a lower ability to form chlorine radicals. So these are being used as temporary alternatives until safer products are developed. Most aerosols now have been replaced by the pump spray systems or use chemicals such as nitrogen as a propellant. Many industrial fridges now use things like ammonia or a hydrocarbon as the coolant gas, and carbon dioxide is used to make those foamed polymers instead.